We were discussing about the diode. We have seen forward bias and reverse bias of a diode and how a diode works. We have seen the VI characteristics of the diode. These are the prerequisites that are required for studying diode equation, representation of VI characteristics by using diode equation, effect of temperature on diode characteristics, and then ratings of diode. Now today we will see first what is a diode equation. Now we have seen that we can experimentally determine the VI characteristics of a diode, but every time it is not necessary to do an experiment. We can represent or we can obtain the VI characteristics by using an equation called as diode equation. This equation is also known as Shockley's equation. It is under the name of the scientist who discovered this. What he gave the diode equation is that ID is equal to Is e raised to power Vd upon eta Vt minus 1. Now this equation is called as Shockley's equation or simply diode equation. Now let us see what are the terms involved in this equation. This first term is ID. ID is nothing but IF, that is forward current through the diode, the forward current that flows through the diode, which is typically in milliampere. Is is nothing but IR, which is the reverse saturation current, and it is in the order of picoampere or nanoampere for practical diode. Reverse saturation current is a function of temperature. Okay. Now this E is an exponential term that we use in mathematics. E. Vd is nothing but Vf, that is forward voltage drop across the diode. For silicon it is 0.7, we know. Now let us see the other two terms. Eta is ideality factor. Eta is 1 for germanium and eta is 2 for silicon. Now this ideality factor, it depends upon the type of material, the condition in which experiments are performed, and many other terms. So but for time being we can consider eta is ideality factor and eta is equal to 1 for germanium and eta is equal to 2 for silicon. Now in this equation there is a term Vt. Vt is nothing but thermal voltage. Now what happens is that with the increase in or decrease in temperature, it affects the resistance of a diode, because we know that diode is a semiconductor device and every semiconductor device has negative temperature coefficient of resistance. Therefore we have to calculate Vt. So Vt is given by formula thermal voltage. Vt is equal to kT by Q. Now what are these terms? We will see. K is a Boltzmann constant. And its value is 1.38 into 10 raised to power minus 23 joules per Kelvin. So this is a constant K over here, and T, this T represents temperature in kelvins. So temperature in Kelvin is 273 plus temperature in degree centigrade. What does it mean is that if we put the temperature in degree centigrade over here, we can get the value of temperature in kelvins. So this will give us temperature in Kelvin. Now what is this next term is that Q. Q is charge on electron, that is 1.6 into 10 raised to power minus 19 coulombs. And this is very small quantity. Now how to use this Vt? Let us calculate Vt, thermal voltage at 27 degrees centigrade. That is at room temperature, say. So first of all, we need to calculate the temperature. So T is given by 273 plus 27 degrees centigrade, that is in Kelvin. So it gives us 300 Kelvin. So temperature in Kelvin is 300. Now if we see this K is constant, Q is constant, only variable is T, which changes with temperature. So naturally Vt is going to change with this change in temperature. It is observed that with the increase in the temperature Vt increases, with the decrease in temperature Vt decreases. Now if we calculate Vt at 27 degrees centigrade, what we will get? So substituting the values, Vt is equal to, in that equation, Kt by Q. So K is 1.38 into 10 raised to power minus 23 joules per Kelvin into temperature is 300 Kelvin at 27 degrees centigrade, this divided by charge on electron 1.6 into 10 raised to power minus 19 coulombs. So this is what we get for Vt. So Vt is equal to, if we solve this on a calculator, we are going to get Vt is equal to 26 millivolt. This is but obvious because this Kelvin gets cancelled and joules per unit coulomb is nothing but voltage, and hence the unit millivolt. So this Vt is dependent upon temperature. So at temperature, room temperature of 27 degrees centigrade, the thermal voltage we get is 26 millivolt. If we increase the temperature, then Vt is going to rise. Okay. Now let's come back to the equation. Now how this diode equation can be used to plot a VI characteristics of diode. So let's see it. So we know that diode equation is given by the equation ID is equal to Is e raised to power Vd eta Vt minus 1. I can write the same equation in the form ID is equal to Is e raised to power Vd upon eta Vt minus, if I multiply inside the bracket, so it becomes minus S. So this is the equation I am going to refer. Now case 1, when forward voltage is 0, that is no voltage is applied to the diode, and if we substitute Vd is equal to 0 here, what we get is ID is equal to Is into e raised to power 0. 0 divided by anything is 0, e raised to power 0 minus Is. Anything raised to power 0 is 1. So Is minus Is we get ID is equal to 0. So if we see on the VI characteristics this point, this is Vd, this is ID. So this point is represented at the origin, that is 0. For 0 Vd we are getting ID is equal to 0. Next, if we see second case, when Vd is positive, that is forward voltage is positive, means diode is in forward bias condition. Okay, and then we know at what temperature we are calculating. Let us calculate at room temperature. So if we put in this equation, so Id is equal to Is e raised to power Vd upon eta Vt minus Is. Now this term e raised to power something where Vd is positive is nothing but in the exponential form, because eta is a constant and Vt is constant. We know eta is equal to 2 for silicon, and Vt at 27 degree centigrade is 26 millivolts. We had calculated it earlier. So if we take a look at this, e raised to power 0 is 1, e raised to power 1 is 2.71, like this is the value of e raised to power 2 you can calculate. You can see that it goes on exponentially increasing. So this is the exponential nature. So if Vd increases, this term is going to increase. And what is that? This first term is having significance, and as Is is very, very small, we can neglect the second term, and we get Id is equal to Is e raised to power Vd upon eta Vt. We have neglected this Is because it is very small as compared to this term, and this is going to give us a forward current at the forward voltage, which will be typically in milliampere. Okay, now let's check out the, so this is represented on Vi characteristics by this equation, by this line. So exponential, you can see this is due to the exponential nature, we get like this. So it has to be drawn almost vertical. It should be almost vertical. Okay, so this is by using diode equation. So what you have to do for plotting this is take various values of Vd, substitute in this at a particular fixed temperature 25, and then calculate this and plot the points. When you join the points, you get a diode equation. Due to diode equation, a graph like this. So this is during forward bias. Now let us check out the case. What happens during reverse bias when Vd is negative? So when Vd is negative, so the equation Id, this equation Id is equal to Is e raised to power Vd upon eta Vt. So Vd is negative when e raised to power minus 1, e raised to power minus 2, e raised to power minus 3, because we have seen that reverse voltages in terms are large and they are in terms of minus 5, minus 10, minus 10, 20, like that. So if we substitute this and try to plot, we will see that these approaches, or the higher term e raised to power 10, 15, 20 will approach nearly to 0. So if this term approaches nearly to 0, it is very, very small. If you multiply by this term is going to vanish as it is 0. So you will get Id is equal to, so exponential term, if we want to represent it, is very small point. So it is almost 0. So Id is equal to this 0, near 0, and Id is equal to minus Is we get, because this term becomes 0 and Id is equal to minus Is. That is, now in the diode the reverse current flows, which is reverse saturation current, and we have seen in characteristics that this reverse saturation current was IR or IS, and it was in picoampere or nano. So if we want to plot it over here, so we get a reverse saturation current like this, that is IR, and this is in picoampere or nano. Now this graph, whatever we have drawn, it looks like the actual VI characteristics, but if we compare it with the actual VI characteristics, you are going to see that the dashed is the actual characteristics determined experimentally, and this is obtained by using diode equation. Why it is so? It is because we have not considered the diode internal resistance and the resistance of the terminals. So they are definitely going to add, and you don't get a sharp line but like this. So what is the use? The use is that while solving numerical problems, you can use this equation to solve any of the unknown quantity. For example, forward voltage, forward current is given, temperature is given, you can calculate reverse saturation current. If reverse saturation and all parameters are known, we can calculate the forward voltage. If everything is given and forward voltage is to be calculated, we can calculate that also.